Carnot engine. We discussed this thing, the efficiency of heat engine that comes to eta equal to 1 minus Q2 by Q1, which suggests this thing, the efficiency of engine that is less than 1, it implies that it is less than 100%. So then after so many scientists worked in that particular direction to attain 100% efficiency of heat engine. So many scientists performed so many experiments, developed so many theories, and in those scientists, one was Carnot. He represented one heat engine. Which one was imagined at idealistic level? Say, the Carnot engine, which one is designed by scientist Carnot, so it is known as Carnot engine. It is a piston cylinder-like system. But see, the wall of the cylinder is 100% insulated one. Bottom of the cylinder is 100% conducting one. Piston is also 100% insulated one, and it can move in the cylinder frictionlessly. Clear? Then after, the heat source considered at higher temperature T1, which one is with large heat capacity, it implies that large amount of heat that it can supply. Then the cold reservoir, which one is known as heat sink, at lower temperature was considered with large heat capacity, means large amount of heat, if released in it, then it can absorb. Then after, he designed the cyclic process. Cyclic process means we discussed initial and final thermodynamic state, that is the same one. So Carnot represented the cyclic process which passes through two isothermal and two adiabatic processes. And this particular cyclic process that is known as Carnot cycle. Now, for this particular engine, which he designed, or we can say imagined, he derived the equation for the efficiency of engine. Clear up to this one? Then he considered the working substance. That is the ideal gas. That is the ideal gas. Now, let's discuss the working of this heat engine and prepare its PV diagram. Say, suppose the initial thermodynamic state of the working substance, or we can say system, in which the pressure, that is P1, volume is V1, and the temperature is T1. This one is the initial thermodynamic state of the system. Then first process, so isothermal expansion. Okay, so in isothermal process, the temperature that remains constant. Expansion of the working substance means ideal gas takes place. So volume will increase. If volume increases, then temperature, pressure decreases. Temperature, that is constant one here. So after isothermal expansion, suppose the system reach to the second thermodynamic state, in which the pressure is P2, volume is V2, and temperature is T1. Now, in isothermal expansion, we already discussed the work done. That is, work done W when the system is moved from thermodynamic state 1 to thermodynamic state 2, that is equal to mu RT. Here temperature is taken T1. So mu RT1 ln V2 by V1. And suppose in this particular process, the heat absorbed by the working substance, that is Q1. So this is equal to Q1. This is net heat absorbed, right? So we can say this is equation number 1. Then after the second thermodynamic process, that is adiabatic expansion. In adiabatic process, the heat that remains constant. Now system is moved from the thermodynamic state 2 to thermodynamic state 3, where the pressure changes from P2 to P3, volume changes from V2 to V3, and temperature changes from T1 to T2. And for adiabatic process, we already discussed the work done. So W223, that is mu R T1 minus T2 upon gamma minus 1. Say this one is equation number 2. Now we have to think about cyclic process. એટલે હવે બે વખત આપણે એક્સપાન્શન કર્યું, તો હવે ઇનિશિયલ થર્મોડાયનેમિક સ્ટેટમાં પાછા જવું હોય તો પછી બે વખત કમ્પ્રેશન કરવું પડશે. So third process, that is isothermal compression. So now keeping temperature constant, the system is moved from thermodynamic state 3 to thermodynamic state 4. So P3 to P4, the pressure changes, volume changes V3 to V4, and temperature remains constant T2 to T2. Now work done 3 to 4, that is mu R T2 ln V3 by V4. And now suppose in this particular process the heat released by the system, that is Q2, then we can write this is equal to Q2, equation number 3. Then fourth thermodynamic process, that is adiabatic compression. And with adiabatic compression, now system is moved from final thermodynamic state 4 to initial thermodynamic state 1. So pressure is now P4 to P1, volume is V4 to V1, and temperature is now T2 to T1. Clear? And in this process, we can write the equation for work done W4 to 1, that is mu R T1 minus T2 upon gamma minus 1, equation number 4. Clear up to this one? Now let's calculate the efficiency for this particular heat engine. So efficiency eta, that is equal to 1 minus Q2 by Q1, generalized equation for any heat engine. But here Q2 that is mu r T2 ln V3 by V4 and Q1 that is mu r T1 ln V2 by V1. Mu r cancelled. So we can write Q2 by Q1 equal to T2 by T1 ln V3 by V4 upon ln V2 by V1. Equation number 5. Now for adiabatic processes, we discussed this thing TV raised to gamma minus 1 that is constant. So T1 V2 raised to gamma minus 1 that is equal to T2 V3 raised to gamma minus 1. For this Q2 and Q1 આ બે પ્રોસેસ માટે આ લખ્યું છે હો. એટલે અહીંયા જોજો T1 V1 એવું ના લખી નાખતા. આ જે પ્રોસેસીસ છે એ પ્રમાણે જો અહીંયા આગળ તમારી પાસે ટેમ્પરેચર T1 છે અને વોલ્યુમ ફાઇનલ V2 આવેલું છે. બરોબર છે. અને પછી અહીંયા Q2 વાળું જે ઇક્વેશન છે એમાં ટેમ્પરેચર T2 અને વોલ્યુમ V3 લીધું છે અહીંયા આપણે. બરોબર. એટલે so T1 V2 raised to gamma minus 1 equal to T2 V3 raised to gamma minus 1. Similarly, T2 V4 raised to gamma minus 1 equal to T1 V1 raised to gamma minus 1. So here if we take T2 by T1 that is V2 by V3 raised to gamma minus 1 and here you can write T2 by T1 equal to V1 by V4 raised to gamma minus 1. See, both the equations are of T2 by T1 so we can compare. So left hand side V2 by V3 raised to gamma minus 1 equal to right side V1 by V4 raised to gamma minus 1. હવે જો બંને સાઈડ જો સ્ક્વેર હોય તો આપણે સ્ક્વેર રૂટ લઈએ. બંને સાઈડ ક્યુબ હોય તો આપણે ક્યુબ રૂટ લઈએ. તો અત્યારે બંને સાઈડનો પાવર gamma minus 1 છે. તો take gamma minus 1 root on both the side. So we can write V2 by V3 equal to V1 by V4. Or we can write V2 by V1 that is V3 by V4 equation number 6. Clear up to this one? Now see this equation number 5 and 6. In 6 we proved V2 by V1 that is equal to V3 by V4. So now in equation number 5 this numerator ln V3 by V4 and this denominator ln V2 by V1 will be cancelled because both becomes equal. So finally you will get Q2 by Q1 equal to T2 by T1. Say equation number 7. Now replace Q2 by Q1 in the equation of efficiency of heat engine by T2 by T1. So finally your equation of the efficiency turns to eta equal to 1 minus T2 by T1. Clear? Now see here, at the end of this working of Carnot engine, which one is based on the Carnot cycle, which passes through 4 thermodynamic processes, out of which 2 are isothermal processes and 2 are adiabatic processes. Resultantly, we get the equation of the efficiency that is 1 minus T2 by T1. એટલે જે equation 1 minus Q2 by Q1 હતું એની જગ્યાએ આપણને 1 minus T2 by T1 મળ્યું. But after all, something is subtracted from 1. એટલે ફરીથી પાછું less than 1 efficiency मतलब કે less than 100% આવી. હવે આટલા બધા આઈડિયાલિસ્ટિક લેવલે જ્યારે આપણે ડિઝાઇનિંગ વિચારી જે પ્રેક્ટિકલી પોસિબલ નથી, તો પણ થિયોરિટિકલી આપણને એફિશિયન્સી લેસ દેન 100% આવી, રાઈટ? અને પાછું ટેમ્પરેચરની ટર્મ્સમાં. હવે જો તમારે 100% એફિશિયન્સી જોઈતી હોય તો મેથેમેટિકલી યુ કેન અન્ડરસ્ટેન્ડ ધીસ થિંગ. If you want answer eta equal to 1, then in two ways we can do this thing. Suppose we take temperature T1 that is infinite, then T2 by infinite that is 0, so eta equal to 1. But T1 that is what? T1 that is the temperature of heat source. It implies that we have to find such a heat source which one is with infinite temperature. Practically it is never possible. Okay, let's think second thing. In this equation, suppose we make T2 that is 0, but this one is temperature. So 0 means absolute 0. So we have to think about such a heat sink or cold reservoir, which one is with absolute 0 temperature. Practically it is also never possible. It implies that finally it was concluded 100% efficiency of the heat engine. That is never possible. Never possible. So we can conclude like this: 100% heat energy cannot be converted into mechanical energy. And this naked truth of the nature, that is known as second law of thermodynamics. પછી second law of thermodynamics માટે different scientists different statements આપ્યા, પણ બધાયનું હાર્ટ તો આજ કે 100% efficiency that is never possible for the heat engine. Clear to all of you?